Hi, I'm Troy McClure. You saw me in that last video. Well, guess what? You get me again. All right. So, in our last video, we talked about the idea of what an acid and what a base is, according to those two dudes named Bronsted and Lowry. Okay? That covers a lot of the acids and bases out there. Not all of them, but a lot. And that's a basic one. Okay? It's my favorite of all the acid definitions out there. But at this point now, we're on our second part, chapter 16b. And our objectives are you'll be able to understand that water self ionizes. Water will naturally come apart. What? Yeah, exactly. Now, you're going to be able to understand that when water self ionizes, it forms the bases of the pH and the pOH. Ooh, wait, I've heard of pH before. What's pOH? We're going to get to that. And you're going to be able to calculate and convert between pH, pOH, H3O plus concentration, and OH minus concentration. So that is our challenge for today. This is a fairly juicy one, but this also is going to explain a lot of things. Okay? So with it, now some acids are safe to eat and drink, like sodas, for example, lemon juice, orange juice. Now others are dangerous or deadly. Why? Okay, now that's a very important question. There are some acids you totally stay away from. And then there are some that we can go and we can take it, tomato soup, we can do coffee, right? We can do soda, all right? And that's all cool and everything. Alkaline water, yeah, exactly. So here's the thing. Let's go down to the basics. We got to look at water, good old H2O. Water can react with itself. Why? It's the nature of water that it will break up. A small fraction of water will actually break up with itself. And it's kind of like, it's not exactly like the ending of a Taylor Swift song, like we're never ever getting back together. No, not that. It's just, it'll break up, it'll hook up. Break up, hook up. Break up, hook up. Okay? And that's pretty much it. So what's happening? Well, we have here two H2O, two waters, and you may notice how the arrows are going back and forth. And if you notice the arrow going this way to the product side, it's a little, it's shorter, which means it's telling us that's not happening that quickly. But on the other hand, notice the arrow going backwards, okay, where we're getting the H2Os back a little bit faster. So that's what we have. So water reacts with itself. So two of those H2Os can break off into an OH minus and an H3O plus. Now, some chemists, what they'll say, instead of saying H3O plus, they'll say H plus. Okay, and for some people that might be a little bit easier. Now, here's the thing though. There is an ionization constant of water. And what we've done, it's set at 1 times 10 to the negative 14th at 25 degrees Celsius. You'd say, Canu, there's going to be math in here? Well, yeah, there's going to be some, but here's the thing. That ionization constant is going to form the basis of the pH scale and the pOH scale. But usually you're more familiar with the pH scale. Okay, that 1 times 10 to the negative 14th. Pay attention. So with that ionization constant, again, notice how I put it in big letters. Why do we care? The pH scale comes from the pH equaling the negative log of our H3O concentration. Oh, log. What's log? Is that like, a piece of wood, right? Like I tossed a log into a campfire and stuff? No. That's one kind of log, dudette. But this is a mathematical log, okay? It's kind of like a base 10 thing. I'm not the experienced math teacher here. But let's get to the point though. When we look at pure water, the pH is equal to the negative log of 1 times 10 to the minus 7th molar. Wait, where did you got that? Remember, we're looking at water, okay? And we look at that ionization constant here of 1 times 10 to the negative 14th. Have you noticed that? Now look at the 1 times 10 to the negative 7th. And what do you notice? That 1 times 10 to the negative 7th is the halfway point between 1 and 1 times 10 to the negative 14th. So what are you talking about? What we're talking about, guys, is the concentration of the H3O plus. In that, this is the concentration right here, 1 times 10 to the minus 7th molar. Well, wait. Troy, Mr. McClure, are you saying that that's a really big concentration? No, on the contrary. It's very, very, very small, okay? I mean, obviously, living things need water in order to survive. If the water was acidic, okay, we might have develop some problems. Damage to internal organs. The quality of life not being very good. So, no, it's a very small concentration. So if we know that it's 1 times 10 to the minus 7th molar of H3O, and we're taking the negative log of that, it's saying negative, the log of 1 times 10 to the minus 7th is minus 7. And we know that a negative, because it was a negative log, right? Negative times a negative equals a positive. So that's where we get the pH of 7. The pH of 7 is describing the pH of water. Pure water, okay? Nothing else added to it, just plain water. So in other words, when we're looking at water, it breaks down. There's a little bit of H3O plus in there. There's also a little bit of the OH minus in there as well, okay? Which is what we see up here. This is what happens when the water naturally breaks down. So we have 1 times 10 to the minus 7th of this molar, and here 1 times 10 to the minus 7th molar. They're really, really small concentrations that the general public isn't going to have to worry about it. Because, you know, God created water. He spoke everything into existence, for crying out loud. And you know what? He made water that it's pretty friendly to living things. That would be kind of an important thing. So with that, you got a pH of 7.0. All right. So what does that mean? That's our starting point for our pH scale. Now that pH scale can go down, it can go up. Now there's a limit to how far it's going to go down or how far it's going to go up for what we're doing here in intro or baby chem or general chem, depending how you look at it. Okay. So what do the letters pH mean? It means the power of hydrogen. And this dude here is the guy who came up with that explanation. Okay. So what they're saying is acidic solutions, the pH less than 7, that's more acidic, okay? What is that telling us? The lower the pH, the more concentrated acid you've got in there. When you go above the pH of 7, it becomes more basic, which you also know as alkaline. Hey, where did you hear alkaline before? Alkaline batteries. Yeah, absolutely. So that's where you have a pH of greater than 7. The higher you go on the pH scale, the more base it is and the less acid it is. Wait, are you saying that the acid and the base exist at the same time in the solution? Yes. For what we're doing here, yes. Why? Okay, let's go back here to this. So if we look how water self-ionizes, okay, a little teeny bit of that water breaks apart. So we got OH minus, and we have an H3O plus. Now, the thing is, they're equal amounts, right? 1 times 10 to the minus 7th molar of this, and 1 times 10 to the minus 7th molar of this. If you add them together, you get 1 times 10 to the minus 14th. which matches this. So the H3O plus, is that an acid or a base? Well, if you go back here, Bronsted-Lowry said the acid donates a proton. The Bronsted-Lowry base says the base accepts a proton. So when we look here, okay, this here, the OH minus, it will accept the proton. Guess what? That makes it the base. Okay, and then here, the H3O plus, it's going to give that proton, give that hydrogen ion, and that makes it an acid. So when you have a pH of 7, you have the same amount of acid and the same amount of base. They're equal to each other, and that makes the water nice and neutral, and that makes it easier for us, okay? Water is pretty awesome in that regards, okay? So again, why is it that we care? That whole idea is the basis of the pH scale. I'm not going to have you guys work with log, but I do want you guys to understand how that pH scale developed. Okay? We talked about the idea of the pH scale, and you remember it from baby bio. You remember it from middle school, okay? Anything below a 7 on the pH scale is an acid. Anything above the pH 7 is a base. At pH of 7, that's the middle ground, equal amounts of acid and base. Equal concentrations, 1 times 10 to the minus 7th molar. I told you that chapter 12 was going to come in handy here. That's right. That's exactly it. Okay? So, the pOH scale. So right now, this is the pH scale here. Let's look at the pOH scale. It's kind of like the opposite. In fact, it is the opposite. I'm just saying. The pOH scale describes the hydroxide ion concentration. Okay? It describes the hydroxide ion concentration, that OH minus. So it comes from pOH is equal to the negative log of the concentration of the OH. Say, wait a minute, that looks awfully familiar. Right. When we look at the pH, we said the negative log of the concentration of the HO3. Oh, wait, those brackets. They're telling us it's the concentration of that particular substance. Bingo. Bada bing, bada boom. You got it. Okay? So when we go back, whoops, hey, the pOH is the opposite. It is the negative log of the concentration of the OH minus, which happens to be our base. So because they're opposites, at 25 degrees Celsius, which is the accepted temperature to do these measurements in, pH plus pOH is equal to 14. So if the pH is 7, what's the pOH? 14. Well, if pH and pOH is equal to 14, pH is 7. 7 plus X equals 14. So guess what? The pOH is 7. All right. Keep in mind, acids and bases are opposites. Now here I've got a few of these. Scales here for pH to show you guys. All right. So here is our neutral right here. It's about 7. That is neutral. Now understand, drinking water can range from 6.5 to about 8.5. As humans and pretty much other living things, we can handle that. All right. I don't know what MASH is, but beer and whatever star san is, I don't know what it is. But if you kind of notice when you're going down the pH scale, that becomes more acidic. Now, if you notice, look at the concentration here. This side tells you the concentration. Okay, so that 1 that you're seeing up here, that means 1 molar. Seriously, 1 molar. And when you're down here, notice it's 1 times 10 to the minus 12 molar. So that's a very tiny, tiny concentration. Okay, so this gets into a very interesting thing, that when you're going down the pH scale, there's more hydrogen ions and less OH. That's what makes this acidic. And the lower you go, the more acidic it gets. And it gets to a point where it can do harm to you. Okay? Now, what about if we go the other way? Well, if we're going the other way, it becomes more basic. And if you notice that while it's 7, here it's even. Like, look at the green, look at the blue. They're even. It's fair. Just like between siblings, right? Yeah, had my share of dealing with Thomas and Elizabeth. Yep. Trust me, when I made it fair with them, they both lost. But it was fair. And that's where that pH 7 is. It's fair. Equal amounts of hydrogen, equal amounts of hydroxide, that OH. Now we're going to go the other way. So what's happening? You're getting more OH. And if you notice, the OH is slowly climbing up, right? And the H plus is getting less and less and less. Well, that's why it's becoming more of a basic solution. It's becoming more of a basic solution because the OH is winning. Okay, winning! And the H plus here is losing. That's just the way it is. Now, when you talk about caustic soda, this is not drinking soda. It's not. This is soda used for other things. But I wanted to point out, when you get to a pH of 14, okay, you got a nice 1 molar concentration of the hydroxide ion, and you still have a little bit of hydrogen in there, okay? But the reality is it's such a tiny amount. It's like burping in the middle of a snowstorm. No one's going to hear you when you burp because the snowstorm is so loud. ROH minus is the snowstorm. Your burp is the H plus over here. It's very weak. Nobody's going to know. Nobody's going to care. And there you go. So acids and bases are opposites. All right, let's move on here. So here's another way to look at the graph, and here we look at the scientific notation. So all of these numbers here, you see, think of 1 times 10 to the, okay? So if I go down to a pH of 4, I've got 10 to the minus 4th, which means 1 times 10 to the minus 4th molar. Okay, if I go to pH of 5, it's 1 times 10 to the minus 5th molar. So that's actually less concentrated than the pH of 4. The pH of 4. Okay? Now, stop and think about it for the general public. Okay? What's going to be easier to say? pH or 1 times 10 to the minus 4th molar? And there you have it. So that's why for the general public, we can use the pH. Not that the general public is stupid. That's not it at all. But for the general public, give me the basics, give me what I can use. And pH, brother, sister, that you can use. As gardening, when you want to know the pH of your soil, they do offer tests for that. I'm just saying chemistry in the real world. Okay? Haters can continue hating and chug down that haterade, boys and girls. You're going to need it because there's more to come. Okay, we have to talk about something called strong and weak acids. And for years, that has been abused, okay? So here's the difference. Strong and weak have nothing to do with concentration. It's how well do they dissolve in water. That's it. So strong acids give up protons easily and ionize completely, like HCl. They totally ionize in water 100%. On the other side of the coin, weak acids do not dissociate completely. They don't break apart easily into ions. Maybe 5% if you're lucky. And a great example of that, it's good old acetic acid, which you guys know as vinegar. Yup, absolutely. Vinegar. Weak bases, weak bases are poor proton acceptors. They do not dissolve well. 5% like ammonia. Oh my gosh, ammonia smells. But it's a great disinfectant, isn't it? A strong base, on the other hand, accepts protons readily and dissolves well in water, like 100%. Our example here is NaOH, sodium hydroxide, Whoa, wait, where do we have that? You would know that as lye, Lye, but it is also a main ingredient found in drain opener. How come? How do drain openers work? Really simple. What causes drains to clog? Okay, in bathroom sinks, for example, that's an obvious one. Okay, pretty much soap, shaving scum, soap scum, and hair. So if we have a clogged sink at our house, guess who doesn't get to take the hit? This guy! That's right, this guy doesn't. Okay, the sink's clogged. Ugh. What do we do? You're going to get some of that drain opener, which has got NaOH in it. You're going to pour some of it down there and you're going to wait because the NaOH and the rest of the chemicals are going to sit there and slowly dissolve the hair. Why? Because hair is organic and NaOH loves to tear apart organic things. That's why you don't want to get it on your skin because it will start making your skin feel slippery. And if you ignore it, your skin is going to start to hurt as the nerves are telling your brain, hey, wash me because this hurts a lot. Exactly. And that's the nature of NaOH. Now, ammonia, you got to understand, it also will hurt you in concentrated form. So here's a big idea about strong and weak. They don't mean concentration. It's about how well they dissolve in water. So for example, 12 molar HCl and 12 molar vinegar. One is a strong acid. That's HCl, which you also find in your stomach. The other is vinegar, 12 molar vinegar. Guess what? Both of them are going to hurt you. Okay? They're concentrated, but the HCl is a strong acid. It dissolves very easily in water. Vinegar, on the other hand, is weak, and it doesn't dissolve that much, but both can be quite deadly. So here comes the next thing. If we know that acids can go and give away all these hydrogen ions, how many of them can these acids actually give off? Well, it depends on the acid. So, for example, monoprotic can only donate one proton, like HCl, your stomach acid. Polyprotic, now you can donate more than one proton. So there's diprotic, which can donate two protons, H2SO4, which happens to be sulfuric acid. Again, that's a nasty stuff, not fun to work with, okay? But the next one, triprotic, can donate 3 protons. And guess what? A number of you are drinking it. Yeah, not liking it. It's like dihydrogen monoxide. McDonald's uses it in their soft drinks, but they also use it in their floor cleaner. Yuck, not loving it. But H3PO4 can give up to 3 hydrogen ions in there. 3 protons, boys and girls. It's called phosphoric acid, and yes, you do find that in some of the soft drinks. Like Coca-Cola, Pepsi, those ones. I don't think in Sprite, but your darker colored colas, you'd find those. Okay, we talked pH. We understand it's a scale, okay? But how do we measure it? Well, there's different ways we can measure it. There are universal indicators that can be used. Indicators are substances that the colors are sensitive to the pH change. And that's a visual thing, okay? We can use pH papers. You dip the paper in and it'll turn color because of the presence or absence of certain chemicals like acids or bases. And then you can compare it to the color scale that you see right over here, okay? I've used those before. pH meters are electronic, and it makes it look so much high tech, okay? Not a guaranteed icebreaker at parties, at the high school or college level. I'm just saying, don't use that. Don't go and brag, hey, I know how to use a pH meter. Please don't. You'll embarrass yourself and the rest of us, including your chemistry teacher. Over here, this is the universal indicator. And this one, actually, depending on whether you put the acid or base, it's going to go through the colors of the rainbow. It's so cool. But I actually have a couple of videos where I do get to mess around with it. And I set it to music, too. All right. Oh, come on. Oops. And with that, we're going to stop here on this. So, you know what? We talked about acids and bases. What do they give? What do they receive? We talked about the basis of the pH scale. Okay? Where pH of 7 is neutral. Why did we pick pH of 7 as the neutral? How water breaks itself apart, it ionizes itself. Okay, we looked at the pOH, which is the opposite. We're going to spend time working on that. Okay, but we also talked about strong acids and weak acids, strong base and weak base. Strong and weak have nothing to do with how powerful they are. It just has to do with how well do they dissolve in water. Strong dissolves very well in water. Weak, okay, it's very little in water. Okay, and with that, ladies and gentlemen, this is Troy McClure signing off. Take care and God bless.